First of all, I would like to go over the titration terminology to load you guys with some of the basic vocabulary. First of all, the neutralization reaction. You should know this one already, but a double replacement reaction between an acid and base characterized by the production of water and a salt. Strong diprotic acid will completely dissociate in neutralization reaction. Because we have not covered weak acid or weak base, we are going to just assume that every time you have diprotic or triprotic acid, meaning the acid can donate more than one hydrogen, we'll just for now assume it's going to completely dissociate. Okay, titration. So what is titration? This is a technique used to carry out the neutralization reaction in a controlled way, usually to find the concentration of an unknown acid and base. So titration is by itself is a whole new chapter. Okay, this is an application of acid and base chemistry, and the titration is usually a lab a technique, okay, used to find out the concentration of an unknown solution. Indicator. Indicator is a substance that will give a characteristic color under certain pH conditions. So the usually indicator is going to react to the either acid or base and shows a color to tell us, right, visually whether that unknown solution is acidic, basic, or neutral. Equivalence point. This is a point in the reaction when the acid and base exactly neutralize each other, so that every hydrogen and every hydroxide produced by acid and base are perfectly balanced to produce the water, which is a neutral substance. Titrant. This is a substance reagent solution of a known concentration that is added in titration. So titrant is a substance with known identity and also known concentration that we use to analyze the unknown substance. Analyte is a chemical substance that is the subject of chemical analysis. So typically this is the one with known identity but unknown concentration. Okay, how titration works. First of all, the substance that you can see that filled up the burette, right? These are called a titrant. So again, titrant are known substance and also contains acid or base. It could be one or the other, and also has known concentration. And typically, this is in a lab, you prepare this solution. An analyte that goes here in our Erlenmeyer flask, and this is usually with a known substance, meaning you know the chemical formula, and contains an acid or base, but has to be the opposite from the titrant. So if the titrant was the acid, analyte has to be a base, and vice versa. And this will also contain an indicator, and also this analyte has an unknown concentration, meaning the molarity is unknown, and this is the whole point of doing the titration. Okay, so titrant. Use the valve on the stopcock to add the desired amount of titrant. Okay, now again, titrant is the substance that we control everything. We know the exact volume, we know their molarity, therefore number of moles of hydrogen or hydroxide ions, and we add desired amount by turning on the valve. And then based on the added volume, you can determine how many moles of hydrogen or hydroxide by using the formula mole is equal to molarity times volume. Meanwhile, the analyte, which is now receiving the titrant, okay, and we're gonna go ahead and use the indicator to find out when the equivalence point has been reached, and the color change will let us know the solution now has become the other. For example, let's say that the initial given analyte was on a base, or let's say a base, and then if you add an acid to it, right, acid and base will get neutralized and produce the water. Eventually, when you add enough of the acid, right, from the titrant, you are going to now make the entire solution acidic, right? And that's exactly the when you pass the equivalence point, and those indicator will let us know that you have passed the equivalence point by changing their color. In the beginning of titration, color will show but quickly disappear, meaning that not enough titrant is added to neutralize the analyte. All right, this is when you know the titration is completed. When enough titrant is added, the color will be permanently changed and it doesn't go back. Find out how much volume of titrant is added, right, to permanently change the color. And now you can determine the concentration of molarity of analyte using the titration equation. All right, so let me explain to you a little bit more detail about this whole process. All right, so I'm going to go ahead and use an example of a titration where the titrant is a base. So the titrant, the base, means that they contain the hydroxide ions. If titrant is a base, it will contain numerous hydroxide ions. And analyte, we're going to make it opposite, make it acidic, and they will contain the hydrogen ions. As you open the valve, the hydroxide is added to the analyte, and they're going to drop and goes there, right? First of all, when you add a base to this analyte, indicator is going to react. Again, indicator only reacts to the titrant. So the indicator will quickly change the color because it reacts with hydroxide. But as soon as they react, hydroxide will also react with hydrogen to become the water, which is H2O. And that gets neutralized, and they're not ions anymore. So we keep adding the hydroxide, gets neutralized, keep adding the hydroxide, and gets neutralized. Eventually, when there's no more hydrogen, and then when you add more base, hydroxide, this hydroxide is going to make the entire solution now basic. That's when the color is going to permanently change because the entire solution is basic, and this hydroxide is not going to get neutralized because you ran out of the hydrogen. And then you, using the volume of a base you have added, you can now calculate the concentration of the acidic solution it was initially there. Practice problem. Suppose 22.5 milliliter of 0.52 molarity of NaOH was added to neutralize 75.00 milliliter of hydrochloric acid. Now, what is the molarity of the acid? Okay, the titration equation looks like this. MAVA is equal to MBVB. Okay, A stands for the acid and B stands for the base. So once you know the volume and concentration, molarity of the base, and you know the volume of the acid, then you can basically calculate the molarity of the acid. Well, first of all, I'm going to carry out the equation. Well, we have a hydrochloric acid and sodium hydroxide reacting. This is again double replacement reaction, which will generate the water and salt, which is NaCl. According to the net ion equation, this is essentially H plus OH that becomes water. Everything else is a spectator ion, meaning it doesn't matter what they are. Now, we're going to have to use this equation to calculate the MA because we're looking for the molarity of the acid, or basically the molarity of the hydrogen, because this is what makes it acid. So I'm going to go ahead and plug in my numbers, the molarity of base, volume of the base, divided by the volume of the acid. Again, well, technically, the volume has to be in terms of liters to make this equation work. But as long as you make your volume of acid and base the same unit, it doesn't matter if you use a liter or milliliter. They cancel out each other anyways. Reporting 2 sig big, 0.16 molarity. Question 2. If 37.12 milliliter or 0.845 molarity of sulfuric acid neutralize 40.50 milliliter of potassium hydroxide, what is the molarity of the base? Again, I'm going to go ahead and carry out my equation. sulfuric acid and potassium hydroxide to make the water and potassium sulfate. Now, according to that equation, you should be able to get this equation. Okay. Now, MAVA is equal to MBVB. Now we are looking for the molarity of the base, so we rearrange equation like this. However, okay, MA, the molarity of the acid needs an adjustment. Why? Because every time you have a sulfuric acid that breaks down into the ions, okay, because it's a diprotic acid, you are going to generate twice more hydrogen than usual. Okay, this is diprotic acid. And again, we're going to assume that diprotic acid will completely dissociate and then they will break down into individual ions. Okay, now how does that affect our answer? The concentration of a hydrogen is twice more than the concentration of sulfuric acid because the stoichiometric factor, right, the coefficient is 1 sulfuric acid generates 2 hydrogens. And this molarity of acid is going to be concentration of hydrogen. Since we are given the concentration of sulfuric acid and the concentration of hydrogen is exactly twice of that sulfuric acid, I'm going to go ahead and multiply the concentration of sulfuric acid by 2 and get a 1.69 molarity. Okay, and then you multiply and divide, and you should be getting 1.55 molarity. Titration and pH problem. Okay, these are a little bit more advanced problem. Okay, now you have a 27.8 milliliter of 0.384 molarity hydrochloric acid was added to 32.1 milliliter of 0.453 molarity of sodium hydroxide. What is the pH of the mixed solution? So essentially, well, based on the information, we do not know whether the equivalence point has been reached or not, because I basically give you the volume and molarity of each solution and mix them up. At this point, you do not know if the titration was completed or not to the equivalence point. So you need to first find out whether the final mixture is acidic or basic. You're going to have to first find out the number of moles of acid by multiplying the molarity of acid by volume of the acid, which I do that and I get this number. You do the same thing in terms of the base. Okay, you're gonna find out how many hydroxide ions are in this solution by multiplying the molarity of base and the volume of the base. That will give you 0.015 mole. Okay, this time, yes, you have to use the liters, okay, because the molarity is gonna contain the liters. So now, what does this tell us? The number of hydrogen ions, right, the molarity of the moles of acid is 0.0107 mole, and number of hydroxide ions moles is 0.0145. So clearly there are more base moles than hydrogen, which is acid. So there are more moles of base than acid. Thus, you need to subtract the moles of acid from moles of base to find out how many moles of base are not neutralized, right? So I'm going to go ahead and subtract these two numbers, and I get this number. Now, that means 0.0107 moles of acid and base, they got neutralized each other and becomes a water. And at the end of the day, you only have 0.0038 moles of a base remaining. Everything else became water. Now, I'm going to go ahead and find the molarity of the solution and calculate pH. Well, because the pH needs a concentration in molarity of the base, but this is mole, not the molarity, right? To calculate the molarity, you divide the moles by the volume. So we already found out the moles of the base, so I'm going to plug it on the numerator. Now, the volume is interesting because you are adding these two solutions together, right? Initially, which was an acid and which was a base. When you add them together, you are actually changing the volume of the final solution. So I'm going to have to add the volume of these two solutions and then find out the concentration in molarity of hydroxide ions, which I'm going to go ahead and plug into my pOH equation to calculate the pOH. using two significant figures, and I'm going to have to convert this into the pH level. Again, this is when you get to use the square of the depth, right, from the previous lessons. And then you calculate pH is equal to 14 minus pOH, and 14 minus 1.2 is 12.8. Okay, titration pH problem. This is basically the setup. I have just changed, if you look at this, right, I only changed the volume of the acid. I kept everything the same. I just changed the volume of the acid. So I'm going to go ahead and fast forward. So boom, this time, this is the numbers I get, right? So number of the acid increased. That's because obviously I added more volume of acid. Now, this time there are more moles of acid than base. So that means your total solution, right, the mixture is now overall acidic. Now subtract these two numbers, right, acid minus base, and then I get 0.0037 moles of acid surviving. Everything else, the difference, the 0.0154 moles of each base and acid gets neutralized. Now find the molarity of a solution and calculate pH. We're going to do the same thing. To calculate the pH, we need the concentration in molarity of the acid. So I'm going to go ahead and plug it in the moles of acid, divide by the volume. Okay, now I'm going to add these two new volumes. And then I get this is a molarity of the hydrogen. And then plug into now pH is equal to negative log concentration of hydrogen. That will give us the answer right away. Okay, I hope you guys enjoyed and have a great day.